In this video, we're going to cover similar triangles, mid-segments of triangles, setting up and solving proportions with triangles, so a lot of different things about similar triangles. So to get started, we have three similarity shortcuts, and those are AA, which is when two angles of one triangle are congruent to two angles of another triangle. It shows that the triangles are similar. So in the example here, you can see that there are the two 65-degree angles, so that's one pair of angles. And then there are the vertical angles. Vertical angles are always congruent. Look out for a letter X when you have intersecting lines. And then you have vertical angles. We also have SSS. SSS is when the ratio of the corresponding sides of two triangles are proportional. It makes the triangle similar, so it's all three pairs of corresponding sides being proportional to each other. So you do actually have to check that the corresponding sides are in fact proportional. So if I wanted to check that out over here, I could divide the side from one triangle over the corresponding side from the other triangle. So I just need to see what matches up. So I could divide 4 over 3, those match up. I could divide 8 over 6, those match up. And I could divide 16 over 12, those match up. When I divide these, they should have the same scale factor. And that's about 1.3, 4/3. Let me see if the other ones are the same. And they are. They all are the same. They're a scale factor of 4/3, but for those of you who like to see it with decimal, they're all approximately the same. They all are the same decimal, approximately 1.3. But if you reduce each of the fractions here, you'll see that all of the fractions are 4/3, which is the exact scale factor. So I'm going to write here the scale factor of all the sides is 4/3. So the sides are proportional. Then we have side angle side. And side angle side is when you have two proportional sides with a congruent angle in between, and that shows that the triangles are similar. So notice how we have a congruent 26-degree angle in between the two pairs of sides. So we just have to check that the two pairs of sides are in fact proportional by finding the scale factor, just like we did before. I could do 20 over 12, those correspond. And I can do 15 over 9, those correspond. And when I divide those, I should get the same scale factor. And I got about 1.67 here. And it should be the same, about 1.67. If you reduce them, they should be the same fraction, which would be the exact value. And the reduced fraction would be 5 over 3. So the scale factor of the sides is 5 over 3. That is the exact value. We do like to use exact values whenever possible so that we're not rounding. So we do have side angle side here. Two proportional sides with a congruent angle in between. We have one more way that shows that triangles are similar. It's called side splitter theorem or the triangle proportionality theorem. And what that says is that if you have a line in your triangle that intersects the sides of the triangles and divides the sides proportionally, then you have similar triangles. So basically, if you have a line that's parallel to the base in your triangle, it creates congruent corresponding angles. And there's the shared angle A between the small and the big triangle. So you have AA. So anytime you see a line that's parallel to the third side of the triangle, like this situation, it forms two similar triangles, the small one and the big one, and the sides are divided proportionally. The sides that are intersected are divided proportionally. Okay. Once we show that triangles are similar using one of the similarity shortcuts, we know that the corresponding angles are congruent and corresponding sides are proportional by the same scale factor. That's the definition of what it means for triangles to be similar. So since you know that corresponding sides of similar triangles are proportional, We can find missing side lengths by setting up and solving proportions involving the sides of the similar triangles. And after we set up a proportion, we do solve by cross multiplication. We're going to do an example together in this video of how we can set up and solve a proportion using the sides from similar triangles. So in this example here, we have that EF is parallel to HG. And since we have parallel lines, I see a letter Z, and I know that we have congruent alternate interior angles. Alternate interior angles are congruent when you have parallel lines cut by a transversal. We also do have a letter X, intersecting lines, so we do have vertical angles. And with that, we have AA, so we do have similar triangles here. And since the triangles are similar by AA, we can set up a proportion, involving their corresponding sides. So let's do it. I'm going to take 12, which is the flat part GH. So I'm going to take the flat part from the other triangle, which is 5. So I did a side from the bigger triangle over the corresponding side from the smaller triangle. Not the only way to set up a proportion, but if this is the way I'm setting it up, I need to be consistent on the other side. Side from big triangle over corresponding side from small triangle. The only other side I have from the big triangle is 6.1x minus 6.5, and that corresponds to 1.4x plus 3. Not the nicest numbers here, so hopefully you do have your calculator next to you. So when we cross multiply, we're going to multiply this way first. 12 times 1.4x plus 3. And then that's equal to the product of these two terms, 5 times 6.1x minus 6.5. Now I'm going to distribute. So 12 times 1.4 is 16.8. And 12 times 3 is 36. And then we have 5 times 6.1. And that is 30.5. And then 5 times 6.5. And that's 32.5. And now we just need to solve our equation. I'm going to add 32.5 to both sides. And 36 plus 32.5 is 68.5. And then I'm going to subtract 16.8x from both sides. $30.5 minus 16.8 is 13.7. And then finally, to get x by itself, I'm going to divide both sides by 13.7. 68.5 divided by 13.7 is 5. The x value is 5. Always double check the question. The question is asking for the length of HI. So I do need to plug back in. So I'm going to substitute in my x value of 5. And let's see what we get. 5 times 6.1. And then subtract 6.5. And I get 24. Notice how the x value is an answer choice. They will always do that on Regents questions. The x value will always be an answer choice. Now we're going to talk a little bit about midsegments of triangles. So the midsegment of a triangle is the segment that connects the midpoints of two sides of a triangle. When you do have a midsegment is parallel to the third side of the triangle and is half the length of the third side. So as you can see from the first picture over here, if DE is the midsegment, it's parallel to AB to the side of the triangle it's not intersecting, and it's half the length of AB. Be careful, because not every segment that's parallel to the third side of the triangle will be a midsegment. You do need to be told that either you have a midsegment or that the points are midpoints. And if they are midpoints, they should divide the sides equally into congruent parts. So if this is 4, this should be 4. If this is 8, this should be 8. It should be divided equally if they're mid-segments. So always just double check. If you want to think that the mid-segment is half the base, then just make sure that you actually have a mid-segment. Otherwise, like we saw before in the side splitter theorem, we have similar triangles when we just have a line segment that's parallel to the third side. But if it's not necessarily a mid-segment, we have similar triangles, but we don't specifically know that MN is half of BC. That would be if it were to be a mid-segment. In this picture over here, I want to show you guys that a triangle can have 3 possible mid-segments. DF is a mid-segment because it's joining D, which is a midpoint of side KJ, with F, which is the midpoint of side KL. FE is a mid-segment because F is the midpoint of KL and E is the midpoint of JL. And finally, DE is a mid-segment because D is the midpoint of KJ and E is the midpoint of JL. So they're all segments that are joining midpoints of sides together of the triangles. So there's 3 possible mid-segments any triangle can have. Let's do some examples so we can see how mid-segments work in some Regents questions. So here in the question, we're told that N and E are the midpoints of AG and AL. So we know for sure that NE is the mid-segment because we were specifically told that N and E are midpoints of the sides that they're on. If N is the midpoint of the side that's on AG, then it splits AG into 2 equal parts. And if E is the midpoint of the side that's on AL, then it splits AL into 2 equal parts. We're also told that NE is 15 and GL is 3x minus 12. And what we're looking for is the value of x. Well, since we do have a mid-segment, we know that the mid-segment is half the length of the base. So if I double the mid-segment, if I double 15, then I should get the base or the third side. So now I have my equation and I can solve really quickly. I'm going to add 12 to both sides and I have 42 equals to 3x. The only other thing I have to do here is divide both sides by 3. And I have x is equal to 14. And I'm just going to double check my question. My question is asking me to find the value of x. So this x value is the answer that I am looking for. Over here, I have another example that looks slightly different. In triangle ABC, L is the midpoint of BC. So L is the midpoint of the side BC it's on, so it splits BC into 2 equal parts. M is the midpoint of AB, so M splits AB into 2 equal parts. And N is the midpoint of AC, so it splits AC into 2 equal parts. And since all of these segments here, MN, NL, and ML are made by joining midpoints together of the sides that they're on, these are all mid-segments. So here's an example where we have 3 mid-segments of the triangle. We're told that MN is 8, ML is 5, and NL is 6. And we need to find the perimeter of trapezoid BMNC. So I'm going to just outline that trapezoid BMNC so we could see the sides. Because to get perimeter, we add up the 4 sides. So we already have one side of the trapezoid. We already have the 8, so I'm going to put that here on the side. We do have to find the other 3 sides. So if MN is a mid-segment, it's half the length of the third side, the side it's not touching, the base. So for MN, it's touching AB and AC. So the side it's not touching is BC. So BC would be 16. After we find the 16, we can work on finding the other sides of the trapezoid. So this mid-segment over here has a measurement of 5. So the side that it's not touching is AC. So that should have a length of 10. And since N was a midpoint, it's splitting the side in half. So each of these pieces is 5. So that 5 over here gives us another side of the trapezoid. So far we have this side, and this side. All we have left to find is this side over here, BM. And we can find that because this midsegment is 6. So the side that it's not touching is 12. And since M is a midpoint of side AB, the side is split in half. So the missing piece is 6. So all we have to do now is just add up those sides that we found. 8 plus 16 plus 5 plus 6. And we get 35 to be the perimeter of the trapezoid. Here, I have a bunch of practice questions that we'll go through together in this video. So please pause the video before you see the solution to each of the questions, and that way you have time to think about the question for yourself and to try it out yourself. In triangle ABC and triangle DEF, AC over DF equals to CB over FE. So which additional information would prove that the triangles are similar? I'm going to draw the triangles, triangle ABC and triangle DEF, which you should always do if the question's talking about things like triangles, but you don't see them. So now that we have our two triangles drawn, they're telling us that the ratio of AC over DF, so here's AC and here's DF, is equal to the ratio of CB over FE. So CB is over here and FE is over here. So that's giving us two pairs of proportional corresponding sides already. So what could help us prove these triangles similar is if we were given another pair of proportional sides, AB and DE, and that would be SSS, or if we were given the angle that's in between the two proportional sides that we already have. So answer choices 1 and 2 are not going to be helpful because we don't need congruent sides. We need proportional sides for proving triangles similar. So I'm going to be looking for the answer choice that gives the angle that's in between the two proportional sides. So we could have SAS. So that would be angle ACB and angle DFE. That is answer choice number 3. Here we're given the information that AB is parallel to DFC, that EDA is parallel to CBG, and we're asked which statement is always true. So the first two answer choices are about triangles being congruent, and the second two are about triangles being similar. You need a lot more in order to prove congruence than to prove similarity, because for congruence, you always need a congruent side. All of the congruence theorems, SAS, SSS, AAS, ASA, HL, they all require a side. Whereas for proving similarity, it's often easier because as long as you have two congruent angles for AA, you've proved the triangle similar. So I'm going to start with answer choices 3 and 4. Because if one of those is correct, if we can prove one of those to be true, it's going to be a lot easier than trying to find information to prove the triangle's congruent when we might not even be able to do so in this question. So let's start with answer choice 3. Triangle BAG, so that is this triangle over here at the bottom, similar to triangle AEB. So that's this triangle over here. So we do have the purple parallel lines. So we do have these alternate interior angles. And I'm not seeing anything else we can get between those two triangles. So I don't think those two triangles are going to be similar. For answer choice number 4, we have triangle DEF, similar to triangle AEB. And already I know that that needs to be true because I see side splitter theorem. I see that we have a line segment DF that's parallel to the base to AB. So remember, it creates the congruent corresponding angles. It has the shared angle between the small and the big triangle. So AA, the small and the big triangle are similar to each other. So answer choice 4 is the correct answer. Okay. AB is parallel to DE. And the reason why they're telling us that is because then we have congruent alternate interior angles. And we also have congruent vertical angles. So the two triangles are similar by AA. We're next told that CD is 6.6 centimeters. DE is 3.4 centimeters. CE is 4.2 centimeters. And BC is 5.25 centimeters. And what we need to find is the length of AC. So we need to make a proportion since we have similar triangles, and that way we can find the missing side of the triangle. So I'm going to put X in my proportion, and then I need to put the side that corresponds to it. Be careful when you're looking for corresponding sides. You want to think of if you rotated this triangle to land on this triangle, what sides would match up to each other, and X would land on the 3.4. Oh, sorry. X would land on the 6.6. My bad. Okay. So since I did the side from the bigger triangle over its corresponding side from the smaller triangle, I'm going to do the same on the other side. And I'll take the 5.25, I guess. And that should match up to the 4.2. And now we can cross multiply and we can solve. We have 4.2 times X. And then this way, we have 6.6 times 5.25. Which is 34.65. And then I can divide both sides by 4.2. And I get that our X value is 8.25. And we are looking for the length of AC. And X does represent the length of side AC. So the X value is what we're looking for. And that is the answer choice that we are looking for. In the next one over here, we have that angle ACB is a right angle, and that's marked for us in the diagram. E is a point on AC, and ED is drawn perpendicular to hypotenuse AB. So if ED is perpendicular to AB, there's also a right angle that's created over here as well, just so we have that down. So we have that AB is 9, BC is 6, and DE is 4. And we need to find the length of AE. So I'm going to represent that as X. Now, if I made a proportion to find a missing side of the triangle right now, I would probably mess up because I can't see what corresponds. But if I redraw the small and the big triangle so they're facing the same way, I could, number one, verify that they're similar. And I could also set up my proportion with correctly using the right corresponding sides. But just to see why the triangles are similar, in this small triangle, there's a right angle, and there's a right angle in the big triangle as well. And the small and the big triangle do share angle A together, but we'll see that a little bit better when I redraw the triangles also. So when I redraw the triangles to be facing the same way, I'll just keep the big triangle as is. And then I'm going to redraw the small triangle so it's facing the same way. So that means I'm going to put the right angle over here. And the right angle in the small triangle is at D. And we did say that they shared angle A. So if I put angle A on the bottom left in the big triangle, I have to put angle A in the same spot when I'm redrawing the big triangle because they correspond. And now we can see clearly that they both have an angle A, reflexive property, it's congruent, the triangles are similar by AA. And that leaves E to be over here in our similar triangles. So now we're all set to make a proportion. Let's just quickly relabel the sides using the information from the question. So AB was 9, BC was 6, and DE was 4, and we were looking for AE. And now it's going to be really easy to make our proportion correctly. I'll just do 9 over x, they're both hypotenuses, and then I'll do 6 over 4. And if I multiply this way, we have 36. If I multiply this way, we have 6x. Divide both sides by 6, we have x is equal to 6. Just make sure that you double check what the question's asking for, because 6 is an answer choice here. We're looking for the length of AE, and AE is represented as x, so 6 is the answer choice that we are looking for. We don't have to plug in anywhere. Okay, let's check out this question over here. So they give us a bunch of information about the triangles here, and they're asking, is triangle ABE similar to triangle ADC? So if we're going to explain why the triangles are similar, we need to use one of our methods, SSS, SAS, or AA. And what I'm seeing here is that if we just draw the small triangle and the big triangle separately for a minute, so here's AEB, the small triangle, we have the 5.6 and we have the 4.1. And here's the big triangle, ADC. We have side AD is 5.6 plus 3.42. Let me add that. 5.6 plus 3.42 is the full side, 9.02. And then AC, we have it's 4.1 plus 8.22 to get the full side. So that's 12.32. So from the information that we have here, we already have 2 sides from each of the triangles. So if we can show that those sides are proportional and we can show the angle in between is congruent, then that would be SAS. So the angle in between is A in both of them. It is shared between the 2 triangles, so we can say that it's congruent to itself by the reflexive property. So all we have to do is just show that the sides are in fact proportional, and we can do that with making a proportion. So AE from the small triangle is 5.6. AE is the first and third letter, so it corresponds to the first and third letters here, which is AC. So it corresponds to 12.32. Be careful with that. Use the letters of the triangle in the names to see what corresponds if they provide you with it. AB is 4.1 from the small triangle as well. And AB is the first 2 letters, so it corresponds to the first 2 letters, which is AD, which is 9.02. Let's cross multiply and let's see. So 5.6 times 9.02, and I got 50.512. And then on the other side, 4.1 times 12.32, and I got the same thing. So it checks out. The sides, the corresponding sides are in fact proportional. So we can just write this down. Since angle A is congruent to angle A by reflexive property, and since, a short way of writing that the sides are proportional is we can write that AE over AC, so that ratio was the same as the ratio of AB over AD. The triangles are similar by SAS. And we have our work over here that justifies it. And we have our explanation in words, so this would be a full credit response to this question. Over here, we're told that DA is parallel to AC, so already I'm seeing a side splitter situation where we have a segment DE that's parallel to the base to AC. So we know that it creates similar triangles. We know that the small triangle at the top is similar to the whole big triangle ABC. They tell us that AD is 8, that DB is 4, and that DE is 6, and we need to find the length of AC. So we're going to make a proportion involving the corresponding sides from the similar triangles. It's really helpful sometimes to draw the triangle separately. So this is the small triangle DBE, and we have this side is 4 and this side 6. And this is the big triangle BAC. BA is 4 plus 8, which is 12, and we're looking for AC. And now we could make a proportion really easily. I'm just going to do 4 over 12 equals to 6 over x. We have 4x is equal to 72. And then we could divide both sides by 4. And we get x is equal to 18. And we are finding the length of AC. AC is represented by x, so 18 is the answer choice that we're looking for. We don't have to plug it in anywhere. Using the information below, which set of triangles cannot be proven similar? So let's see. Number 1 might be SAS if the sides are in fact proportional. So let's see, 12 over 4, is that equal to 9 over 3? So here we have 36, so those are proportional. And we do have the congruent right angle in between. So these can be proven similar by SAS, so not answer choice 1. For answer choice 2, we have AA, so those can be proven similar. We have 2 congruent pairs of corresponding angles. Oh, for number 3, that one's pretty obvious because for SAS, you need the angle in between the 2 sides. So the angle would have to be here and here. So this is the answer choice that we're looking for. The reason why answer choice number 4 is not the correct one is because they're congruent triangles by SAS for congruence, but congruent triangles are similar. The sides just have a scale factor of 1, but they are similar. Okay, here we're given that angle D is 65 degrees and that angle EBC is 115 degrees. And the reason why we're given this is because these angles are supplementary. So that means they make 180 degrees. So if we do 180 degrees minus 115, this is also 65. So we have congruent alternate interior angles. And also we have vertical angles, which are always congruent. So we do have AA. So the triangles are similar. So we can make a proportion in order to solve for a missing side. We're looking for the length of CB. So I'm going to put an X on that. And we're just going to be careful because they don't give us the names of the triangles here. We're going to be careful that we do put the corresponding sides together. So we're going to just imagine rotating this triangle so it lands on this triangle so that the angle with the mark on it lands on the other angle with the mark on it. So 7.2 is going to correspond to the X, and 9.6 is going to correspond to 21.6. And then we can cross multiply 7.2 times 21.6, and that is 155.52, and that's equal to 9.6 times X. And then if we divide both sides by 9.6, we get 16.2. And CB is what we're looking for. And we did represent CB as X. So that is the answer choice that we are looking for. A couple more questions left in this video, just a few more. So we are told that the 2 triangles, the big one and the small one, are similar. And it's asking which measurements are justified by this similarity. So let's try out the answer choices. So AD is 3, AB is 6, AE is 4, and AC is 12. And let's see if this is proportional. So I'll just do 3 over 6, and let's see if it's equal to 4 over 12. I already don't think it's going to be. 12 times 3 is 36. 6 times 4 is 24, so that does not work. So answer choice 1 is not the correct answer choice that we are looking for. Let's try out the next one. AD is 5, AB is 8, AE is 7, and AC is 10. Let's check it out and let's see. I'll just do 5 over 8 equals 7 over 10. Oh, nope. That doesn't work out. So answer choice 2 is not the answer choice that makes the corresponding sides proportional. So let's try the next one. AD is 3, AB is 9, AE is 5, and AC is 10. I don't think that one's going to work out either, but let's check it out. 3 over 9 equals to 5 over 10. And nope, we have 30 is equal to 45. So that does not work out. So our correct answer is our last one, and let's see why. We have 2 and 6. We have 5 and 15, and we see it's going to be a scale factor of 3. You can set up the proportion just to see if you wanted to. That's 30. That's 30. It checks out. Answer choice 4 is the correct one. Over here, it's telling us that ES is drawn parallel to AT. So we have side splitter theorem. So the small triangle is similar to the large triangle. And it's asking us which statement is always true. Remember also when you have a line parallel to the third side, it splits the side proportionally. So like CE over EA would be proportional to CS over ST. So let's see if that's an answer choice. CE over EA equals to CS over ST. And then we're all done. And last one for this video, we have AC is parallel to BD. So that gives us congruent alternate interior angles. And then we also have vertical angles, which are always congruent. So the triangles are similar by AA, so we could make proportions with their corresponding sides. So if the triangles are similar, which equation's true? So CE is from the big triangle. DE is its corresponding side from the small triangle, so far so good. The other side should be set up the same way, big over small, but unfortunately EB is from the small triangle, so that doesn't work. AE is from the big triangle. BE is its corresponding side from the small triangle, so far so good. The other side should be big over small as well. AC is a side from the big triangle, and BD is its corresponding side from the small triangle, so that's the true equation.